Bom dia a todos. As únicas palavras em português que vão ter vão ser mesmo as minhas, porque as outras todas, depois o resto da sessão vai ser toda em inglês. Mas eu queria só, para já, agradecer a presença em massa de tantos jovens aqui das nossas escolas e também da nossa universidade, e dizer que que a sessão que vai acontecer dentro de momentos é mais uma das atividades do programa American Corner, que é um programa patrocinado pela Embaixada dos Estados Unidos da América e que está sediado na Biblioteca da Universidade de Aveiro, numa sala que se calhar vocês não conhecem, mas que gostaríamos que conhecessem e que nós vamos criar mais uma série de projetos, com certeza que vocês irão conhecê-los brevemente. Esta sessão tem, como vocês já sabem, a presença de um jovem engenheiro da NASA, Bobak Ferdowsi, que vai ser apresentado aqui pelo nosso professor Carlos Herdeiro, do Departamento de Física, e ele também um astrofísico, que vai, de facto, também dar aqui algumas informações sobre o nosso palestrante. Obrigada mais uma vez, e agora a sessão, como eu disse, vai decorrer em inglês.
Okay, so welcome everybody. It's a great pleasure to have with us today Bobak Ferdowsi. I believe that's how you pronounce it. Is that correct? Okay, good. Who works for NASA. So I was asked to introduce Bobak. It's a pleasure to do so, although we've just met. So I'll say a few facts about him. Bobak was born in 1979 in Philadelphia, in the US, United States. And he grew up both in the US and in Japan. He's of Persian descent, and actually his surname, Ferdowsi, is that of a famous Persian poet who lived about 1,000 years ago. He studied aerospace engineering at the University of Washington and then also at MIT, Massachusetts Institute of Technology in Boston. And in 2003, Bobak joined GPL, Jet Propulsion Laboratory. That's a center for robotic exploration of the solar system, which is managed by Caltech, the California Institute of Technology, for NASA, and started working on the Mars Science Laboratory mission, which eventually led in August 2012 to the successful landing of the Curiosity rover on Mars. During the landing, of which Bobak was the flight director, a task like, well, this was said by Bobak himself, like that portrayed by Ed Harris in the Apollo 13 movie, for the ones of you who have seen it. He wore this mohawk hairstyle, which he still has at the moment, which was quite a contrast with the stereotypical image that some people might have of NASA Flight Control Center scientists with the white shirt, the tie, the rim glasses. And which probably is not true anyway for most of them at the moment. Well, anyway, these together with his charisma made him a celebrity, a fact about which Bobak said, if my mohawk gets a few more people excited about science and this mission, it's awesome. So I believe that's why he's here, to get a few more people excited about science and space exploration. We are quite excited to have you here. Thank you for coming, and we look forward for your presentation and also to tell us about the Europa Clipper mission you are currently working on. So thank you so much. Thank you.
Thank you guys so much. Thanks everybody for having me here. So yeah, let me tell you a story about Mars, how we got to Mars, why it's interesting, and then I'll tell you a little bit about what's happening in the future of NASA. Feel free to ask questions if there's things that aren't clear. Certainly lots of time at the end for a question and answer too. So let me tell you about why Mars, and so I like to start with this photo. So, you know, Mars we've been able to see for a long time with telescopes in the night sky. It has features that are very visible from Earth. You know, in early science fiction, there's stories of people living on Mars, of Martians, of course, of these networks of connected, canals, as they call them. And so for a long time, people were really interested in going to Mars and exploring Mars. And so when we first sent our robotic missions past the moon and onto the, out into the solar system, the first place we visited was Mars. And this is one of the very first pictures we took of Mars with the Mariner missions. And it actually doesn't do much to dispel the idea that there are canals. If it looks like to you that maybe these are networks of connected rivers or canals, sure enough, it still looked like that from the first images of Mars. So it wasn't until the 1970s when we went and decided to actually put something down on the surface of Mars that we were able to really investigate what the planet was like. And still, even at that time, we said, well, Mars, looks like rivers, it looks like life. Let's send a mission to look directly for life. And so in 1976, we landed a pair of Viking missions on Mars. This is Viking 2. And the Viking missions were very ambitious. They decided to look directly for evidence of life. And so they took soil from the ground, they put it into a series of instruments on board the lander, and looked for evidence of metabolism. In other words, that life would create some sort of carbon dioxide or something that showed that life was the process. And sure enough, believe it or not, they actually found it. The instrument said, look, there's a process here that can't easily be explained by chemistry. And some of the science team said there must be, bacterial life, microbial life on Mars that's doing this. But there was one instrument, a mass spectrometer on board, that said there was no evidence of organic chemistry. And on Earth, we know the answer for life is organic chemistry. So it was one of these questions that we said, well, it's not, we don't understand this. There are some chemical processes that could explain what's happening in these life detection experiments. And so we kind of walked away from Mars with this very uncertain answer. Yes, we couldn't confirm life, and no, we couldn't say it didn't exist either. And so for a long time, we said, well, let's not go back there because it's just too confusing. But in the 90s, scientists said, well, listen, it's still an interesting place. Let's go and let's build a scientific case step by step. And one of the first steps was to demonstrate that we could do missions on Mars robotically and drive them around. And in 1997, on July 4th, we always pick nice American holidays, if we can, we landed a small car on Mars. This car is about this big, about the size of a microwave maybe. And it proved that we could actually drive on Mars. It was just a very simple demonstration. It only could drive about 10 or 20 meters away, not very far. But we showed that, okay, this is possible. And as a kid, I saw this, and I was thinking, that is so amazing. It's like driving a remote control car on Mars. It's probably like a video game that they get to play at work all the time. I want to go play video games at work. Let's do this. This seems like a good career choice. And if you look here, you can see the way they landed. Kind of interestingly, they landed with airbags. So they came in the atmosphere, they went on parachutes, and then what they do is they inflate airbags like you find in your car, and then they just drop on the ground and hope for the best. Maybe not the best way of doing it, although it worked. It worked 3 times, so who am I to judge? One of the other things that we followed on with this mission in 2003 and 2004 is we asked the question of, we know life on Earth requires water. Let's look for evidence of water on Mars. And so with those missions in 2004 that landed, we said, yes, there was definite evidence of water in Mars past. So it came to the early 2000s, we were starting to develop this bigger mission, and we were going to answer the question after water, which is, could Mars have ever supported life? Or could it support life today? So the question of habitability. And so this is what I ended up working on. So this Mars Curiosity mission. The ring that you see kind of on your left-hand side there with the little segments, that's the part that I worked on the most. It's called the cruise stage. It gets us from Earth to Mars. It's maybe a 400 million kilometer journey, and we know how good we are at driving this vehicle essentially from Earth to Mars, that we actually can place ourselves on the top of the atmosphere to within 10 meters of where we want to be. So imagine that kind of accuracy without GPS or anything else. We have to use the stuff that we have here on Earth to point at Mars. Now, sadly, that part that I worked on for about 4 or 5 years is very unceremoniously dumped off 20 minutes before we hit the atmosphere, and it smashes into the surface of Mars. So everything that I worked on is now a piece of pile on Mars. But I'd like to think that I did his job very well. It got us there safely. How many of you guys saw the landing? Because if you think airbags are crazy, I'm going to show you, I think, what really crazy looks like. Okay, so here's a video of the landing. I'll just kind of narrate this for you guys. I'll be looking here because I have it on my screen too. So we are now about 7 minutes away from the landing. It takes 7 minutes from the top of the atmosphere to get to the bottom. And what's amazing about this is Mars is actually 14 minutes away at the speed of light. So if you imagine all of this stuff, from the time we hear the first signal, has actually been done for 7 minutes. So imagine taking, the most crazy test of your life and not knowing for 14 minutes how you did. And so we hit the top of the atmosphere, and we're going about 20,000 kilometers an hour at this point. And the goal is, of course, to land safely, slowly, softly on the surface of Mars. And what we do is we basically hit the top of the atmosphere with this aeroshell, we call it, and this heat shield. And the heat shield protects us from the friction in the atmosphere. And right now, the spacecraft is experiencing around 10 times Earth's gravity in terms of deceleration. You can see that here. And also, the surface temperature is getting to about 1,500, 1,600 degrees Kelvin. Meanwhile, we're also flying through the atmosphere. This is the first time we've done that. It's the same way the Apollo missions did it. They flew through the atmosphere. They actually guided themselves, as opposed to just entering and blindly going in. And then as we slow down a little bit, we're down to about 2,000 kilometers an hour, we open a parachute. This is the largest supersonic, meaning faster than the speed of sound parachute ever built. Anywhere that we know of course. I mean, you could say maybe other aliens have built bigger ones, but as far as Earthlings have built, that's the biggest we've done. So we get rid of the heat shield in front, and we use a radar to look for the ground, and as soon as we find the ground, we drop out of the back of the heat shield and kind of free fall with our rockets for a little bit until we're safely away from the parachute. What we want to do is move away so the parachute doesn't come down on top of us. So we're on what we call propulsive descent all the way down, and about 100 meters above the ground, we separate from the sky crane, or the descent stage as we call it, and then we slowly lower both of them to the ground until we touch down very softly at less than a meter per second. And then once it detects touchdown, the descent stage flies off and crashes into Mars. And the rest is a lot of adult men and women crying and celebrating. And I think it's totally fair to cry if you've worked on something for this long and it works. So, but if you thought airbags was crazy, I think that contraption that looks like one of those things that you build as a kid, like a Rube Goldberg contraption where, the domino knocks this thing and then another thing falls off and then eventually the marble gets up the thing. That's what this felt like to us. These are people celebrating. A lot of those are friends and family of the engineering team. I love this moment because it's a picture of the parachute and the aeroshell taken by a satellite that's also orbiting Mars. And it's one of now we have 7 missions at Mars. So it's one of those 7 missions. It's an orbiter called Mars Reconnaissance Orbiter. But it's amazing to me to think that we both have one vehicle that's plummeting towards the surface and another vehicle that's flying overhead, and yet we're still able to actually coordinate those two things to take a picture like this. Another part is, this is the heat shield. This is the part that protected us on the way in. It's now falling away from the spacecraft. We have a camera that faces down while we do the landing. And the white kind of section that you see there, that's a wedge, that's a calibration target, so we know what the camera's seeing and we know what the white balance is. And then there's some cables in there that you can see. Those cables kind of relay temperature and pressure and velocity data to us. And then finally, the white stuff that you see in there, that's like little streaks of white stuff, that was unexpected. That's carbon dioxide that's formed as we landed, or as we entered the atmosphere. So we didn't actually expect that part, so there's always fun stuff to find on your way to Mars. Luckily, none of that broke off in a way that caused any problems for us. And here's the descent stage. So this is the part where we're on what we call a sky crane. We also sometimes jokingly call this hope on a rope, because we're all very hopeful this part worked. And many people, when they saw it for the first time, including myself, thought this was a little crazy. But it works very well. And the reason it works very well is because this is actually a problem that we can solve very easily. In your introduction to physics classes, you often will take a pendulum equation, and you'll look at pendulums. It's a lot easier to model a pendulum, and it's a lot easier to control a pendulum than imagine the other way around, which is me trying to balance, for example, this on my hand. It's a lot harder. So we changed from what we used to do, which is putting rockets on the bottom and keeping the mass on top, to putting the mass on bottom and keeping the rockets on top. And why did we do that? Well, one of the reasons we did that was that radar system likes to look at a nice soft ground. We need to know where the ground is relative to us. So if we kick up a lot of dust, it's hard for us to actually tell where the ground is. And the second part of that is we were afraid that if we landed in some very soft terrain, very sandy or dusty terrain, that we might actually blow ourselves into a kind of a hole. so that the engines would come down below us, and then we would be sunk inside this thing, and it would be very hard for us to get out of that regime. So this is what it looks like, the camera again from the bottom of the rover looking down, and this is what the rocket engines look like on the surface. So it's not too bad. You can still see the ground very clearly. The end result is what we call a crime scene. We make a mess of Mars. I guess it's unfortunate that we pollute another world in order to land there safely. But you can see Curiosity in the middle. There's a little dark spot around there because the engines have blown away a little bit of the surface dust. You can see the heat shield down here in this corner. That's the part that protects us on the way in. The back shell and parachute are connected together off on the other side. And then up at the top, you see the sky crane where we made a big mess. And that's because we had about 130 kilograms of propellant left when we landed. That looks like this in the end. So it's a nice big splat. So why did we go there, of course? And I said a little bit, the idea was to investigate Mars as a potential place that life could have survived or could survive today. So that's the part, the question that we were trying to answer with this, kind of following the water, as we call it. And we have 10 instruments contributed from around the world. Those instruments come from Canada and Spain and France and Russia, along with the United States. And those help categorize that environment. I like this one because it also says one of the interesting things that we brought down there, which you can see is the drill. And in fact, that little bottom part, that lower left there, that sits on the end of the arm, it weighs more than that entire rover that we landed in 1997. So that's kind of how we've scaled up these rovers. In fact, Curiosity itself is about the size of a Mini Cooper. So it's a pretty big rover. And then many people think, wow, that must be such an amazing computer on board your laboratory. Turns out it's not very amazing. It turns out it's really maybe 2003, like really good stats, but by 2012 when we landed, and the iPhone 5 was there, you can tell that it's not quite as powerful as you might imagine. But to our advantage, this is a lot better than Viking had in 1976. Viking in 1976 landed on 18K of memory. So us having 2 gigs of storage and 128 megs of RAM, or 256 megs of RAM, that's amazing compared to what Viking had. Where you see the big advantages is we have a lot bigger batteries, and instead of having to charge our phone, several times a day, we have a nuclear power source that gives us 110 watts a day, or 110 watts, and therefore we can charge the batteries when we're asleep, and use both the batteries and the nuclear power source when we're awake. In addition, we get some pretty good data rates. We have, again, 2 ways of communicating. One is directly to the rover, or to and from the rover, using the rover's antenna. It's a very small antenna. And then, otherwise, we can communicate with one of the orbiters overhead, and those give us much better data rates. So typically, the way Curiosity works is every morning it wakes up, roughly 9 or 10 a.m. Mars time, and then we give it a set of commands to execute for the whole day, and then at 3 to 5 p.m., is when the orbiters pass overhead. So we talk to the orbiters, we send up all the images and all the science and all the driving data that we took, and then the team gets that data, assesses the data, and plans for the next day. So it's very much driven day to day by a mission of discovery. We do have long-term plans. We know we want to go to certain places or we want to do certain things, but for the most part, it's very much what did we find today and what should we do about that tomorrow, which is rare for space missions because most missions know where they're going to be at a given time in the future. They're orbital missions, so they know exactly where they'll be. This was one of the first panoramas we took. So this is right at the landing site, and that's Mount Sharp in the distance. This is actually the reason why we landed where we did, is we wanted to actually go to Mount Sharp. You can tell we're actually pretty far away. At this point, I think we're about 7 kilometers away from the mountain. And you may ask, why didn't you land closer to the mountain? Well, the engineering team likes to pick nice, safe places to land. We want flat, we want minimal rocks, we don't want a lot of slopes like crater walls or mountainsides. And that's because we want to come down safely, very flat, not worried that the rover is going to be like this when we land, not worried that there's going to be a rock underneath us when we land. And so we have to pick an area based on the size of the landing ellipse. So previous missions, when they didn't guide through the atmosphere, they had a landing ellipse of basically 200 kilometers in the long track. Our landing ellipse in the long track is 20 kilometers, so much smaller. But we still have to place it enough away from the mountain so it wouldn't overlap. And here's a little bit about Mount Sharp for reference, I guess. It's about 5.5 kilometers above what we call sea level on Mars. There's no water, of course, so We determine sea level basically by saying, here's what the average altitude of Mars is, that's sea level, and then everything else is above or below that. And this is a zoom in of that same panorama that we took. So this is Mount Sharp. I like this picture because you can very clearly see the layers of stratigraphy in the rock. Those layers basically tell us a time-ordered history of Mars. Each one of those layers represents a different period in Mars' past. So science team loves this stuff because they can actually tell you what's happening on Mars in different periods. Another place you see that on Earth, for example, is the Grand Canyon. So here's where water's carved away this stuff, and you can see again, layers have formed over time, and each one of those layers is a different period in Earth's history. Here's a zoom in of that. Again, a different little section. Again, the layers are very clear, and then the black stuff near the bottom is actually material, very much like volcanic material, that's been swept up against the bottom of the mountain. So it's a different layer itself. One of the reasons why we chose this area is because we thought from orbital data that there must have been a lot of water here. And so we're kind of in the bottom of a crater called Gale Crater, and in the center of this crater is this giant mountain, so it's kind of cool looking. And if you look here, we can kind of see from the orbital images we've drawn on there where we think there was a breach in the wall and where water would have flowed into Mars, into the crater at some point. And so we said, hey, this is a good place to go. If, where there was water, maybe there'll be chances for other ingredients to be brought from other places on Mars, and therefore contain all the goods that we want to find. And sure enough, about 4 or 5 days after landing, we drove past a site called Link. It's a conglomerate. So if this reminds you a little bit of maybe sidewalk or cement or asphalt that's been broken up a little bit, that's exactly what it should remind you of. Both of those are formed in the presence of water. So we know here already from looking at these, just looking at the images without doing chemical analysis, that this must have been formed in the presence of water, and that water would have been anywhere from ankle high to waist high. So you can imagine 4 billion years ago on Mars, you're there, it's cloudy skies, there's a lake that you can walk through. That's amazing to me to think about that image of Mars at one point, because today it's such a different place. And in addition, we wanted to take some samples. We want to make sure everything works on the rover. So we found a little area, a sandy area called Rock Nest. It's basically, there was actually a little trail of rocks that kind of looks like a fire pit, and sand had been swept in there. So we looked to make sure it was deep enough to scoop, and we try that with the wheel. And we measure the depth, and then we can go with the scoop. And sure enough, here's Curiosity there. There's the trench, the same picture that you see on the lower left, and just on the left there of the rover are the 5 scoops that we did. And why did we do so many scoops? Well, because it turns out, not that we knew that we were going to do this so well, but when we did our first breath of Mars, when we inhaled a little bit of Mars, we actually noticed that it looked a lot like Florida, where we launched from. And that's because we had actually trapped enough air inside the instruments that it still looked like Florida after 8.5 months of getting to Mars. So we wanted to make sure that we coated the interior of the rover and all the surfaces with a little bit of Mars to basically dilute or negate any effect from Florida. Some of you might ask, how do you do a selfie at Mars? It's a good question. So what you're missing here, what you can kind of see coming out of the rover a little bit, is we have a 2-meter long arm that can take, the end of it has that turret that has a drill and everything else. It also has a camera at the end of it. And so what we have to do in order to take one selfie is actually take 55 pictures like this until we get the entire rover in view. It's not like where people on Earth take 55 pictures and they choose the best one to post to Instagram. A little different. Here's the first drill that we did at Mars. What's kind of incredible about this, and I hope you guys will appreciate this too. I mean, I used to always think of Mars as the red planet. It's got the oxidized surface. But what's amazing is as soon as you drill just a couple centimeters into the rock, you see a very gray Mars, very different Mars from the Mars that we're kind of used to. And that's one of the reasons why we brought a drill. We hoped that the drill would allow us to tap into parts of Mars that had been preserved in a way that the surface had not been. So we know the surface sees a lot of radiation. We know there's oxidation on the surface, essentially that it's rusting. But bringing a drill allows us to go a little bit beyond that top layer and look down into what's stored in the rock. And we have a number of instruments to do that. So here's an X-ray diffraction and X-ray fluorescence instrument called ChemIn that helps us tell what the elemental composition of things are. I'm going to skip this one. We have an instrument that tells us the weather on Mars. In fact, you can actually look up what the weather on Mars was at any time, which is kind of amazing to me. So we have like a weather report every day. As you can see, the highs and lows aren't great. We barely get to about the high we've ever seen, I think is about 8C. So not a very warm Mars, and at night it gets very cold, down to about minus 80, minus 90. But not crazy. I mean, if you had enough clothes on, you could live on Mars. You would need air. We also carried a radiation detection instrument to help us for human missions to Mars. We want to understand, if humans ever want to travel to Mars, what sort of radiation they might experience. And what we found is that it's a little bit more than we would ideally like to see humans have. So right now, the requirements for the astronauts, this would put them slightly over that for a trip to Mars and back. So we need to find a way of protecting humans if they go to Mars. We also have the ability to breathe in the atmosphere of Mars. I told you kind of the first time we did it, it looked like Florida. Afterwards, when we did it, we saw that it was a little different. Again, carbon dioxide, which I think most people were aware that Mars has a lot of carbon dioxide. But what was surprising is that we found such a heavy amount of argon. That was a surprise. One of the other things that we looked for and that we're still looking for is there were some reports of maybe having methane on Mars. And methane can be formed geologically or biologically. But so far, our ability to detect down to, and we detect down to 1.3 parts per billion, we have not seen any evidence of methane yet on Mars. We still love to. And the SAM instrument on board is a mass spectrometer as well. So what we can do is we heat up the sample, and we're looking for volatile organic compounds, and then we can see those released at time. You have a question? The air pressure is about 1/100th of Earth at sea level. Yeah. So it's about what you would see at about 100,000 feet on Earth. The end result of those scientific analyses, actually at the very first place that we drilled, which we weren't intending to drill when we got there, it's a little bit actually in the opposite direction from the mountain. But one of the science team members said, hey, I think this is interesting, we should go investigate. It's a site called Glen Elg. So we drilled once there, and what did we find? We found that actually, yes, Mars was habitable. So not only did we find the evidence of water that we knew we could see from orbit, but we actually found evidence of chemistry that we know that life on Earth could survive in. So the water on Mars was basically like fresh water. It wouldn't have been too salty, it wouldn't have been too acidic or basic. It had dissolved in it the right chemistry that we know life on Earth can survive on. So that tells you 4 billion years ago, Mars was a habitable place. Life could have survived. Now the question, of course, is Mars still habitable? That remains to be understood. But to tell you now that there's 2 places in your own solar system that life could have survived in, that's pretty amazing. But ultimately, the goal was to get to Mount Sharp. So let me tell you a little about that story. One of the interesting things that came up, and this is always amazing to me about really the space exploration business, is how we learn to do things sometimes after we've launched the mission, meaning that they weren't intended to be used that way, but we find clever ways of using instruments or solving problems that we didn't know we could, when we made the mission. And one of the people realized that by using the mass spectrometer, we can actually look for isotopic ratios. And that also then gives us an insight into how old different parts of Mars are. So now we have the ability to date actually Mars, which we didn't have before. It's the first time it's ever been done elsewhere in the solar system, so that's pretty exciting. We also had some interesting drives. Here's a Dingo Gap drive. So this is what it looks like when you're on very sandy terrain. If you look on the right-hand side of the wheels, you can see how messy that looks. We couldn't actually drive very smoothly over this, so we kind of wiggled our way across it like a crab would. And then from the orbit, you can see some rover tracks. I don't know how clear that is. Not great. But that little shiny object that you can see down there next to Curiosity, that's Curiosity, which, again, it's kind of great to be able to see your own rover from space. But what looks like nice, smooth, relatively benign terrain from above looks like this from the ground. And that's one of the reasons why we like to send ground missions too, is as good as we are at now ascertaining information from orbit, there's nothing like being able to say, hey, this is what it looks like in orbit, but the ground really looks like this. On Earth, we're able to do that in a number of ways, but on other planets, it's really a first, and Mars is the only place we've been able to do that. And so this wonderland of really, I mean, it's beautiful, and you can see a lot of windswept rocks. So we know that actually a lot of this stuff probably was covered for a long time, has been protected from the Martian environment, and only within the last couple million years, which is relatively recent, a lot of this stuff has been swept away. However, the challenge with that is we weren't really designed to travel all over rocks all the time. And so if you look here, there's a series of kind of rectangular or square holes. Those are intentional in the wheel, but just below that is a big hole in the wheel that's definitely not intentional. It's jagged. So we knew that we had started to break the wheels a little bit. And if you look into the shadows, you can see a crack in the wheel that's also not intentional. So driving on this stuff is not good for your wheels, it turns out. I mean, you wouldn't want to do this in your car normally anyway, but what the experience was that we had to learn for the first time on Mars is that we had previously landed in these sort of big plains. And the rocks that we found basically got pushed into the ground when we drove over them. But with Curiosity, we were finding that, one, the rocks weren't moving. I mean, none of these look like they're about to go anywhere. And two, that the way we were driving, essentially we drive kind of like a Jeep. So it's 6-wheels drive instead of 4-wheel drive. And all the wheels are pushing forward. And we allow the front wheel to basically climb a rock while the back 4 push it into the rock, which is great for climbing things, but it also means that your front wheels experience a lot of force. And so that force against those kind of, again, the sort of sharpish edges of those rocks was causing us to puncture the wheels. So we actually had to learn to drive backwards a little bit too. So now we're practicing driving backwards and forwards. And then very recently, within the last week or so, we made it to the foothills of Mount Sharp, to an area called Pahrump Hills. So that's the kind of the hill formation there. This is like a foothill of Mount Sharp. And so we decided to use the drill. I like this picture because you can see the drill very clearly. And sure enough, here at Pahrump Hills, Mars is different. Now you see, instead of the gray rock, you see a sort of chocolate-looking like cocoa powder kind of material. And that actually baffled the science team. When they saw this, they were like, that's not what we expected. And one of the great reasons why we go to Mars to explore is because we have questions, and sometimes we have expectations, and it's not the same. So we've just done the first analyses of this rock, and still the science team is actually very curious about the results, and there's a lot of disagreement on the team about what would have formed these types of materials. The results of this won't be published till probably December, so that's when you'll be able to hopefully hear about it. So there we are at the top at Pahrump Hills. You can kind of see this is Mount Sharp from above, and you can see that we're going to drive slowly through this area called Murray Buttes. The buttes will look like the Grand Canyon, absolutely beautiful. It's actually the early pictures I showed you are of Murray Buttes. And the reason we're doing that is we were slowly going to climb the mountain. So this is what that track looks like. So you can kind of see where we started on the crater floor. So mostly stuff that came from just what had settled out from where that water source was in the past. Now climbing up the mountain, and from a different perspective, that looks like this. So you can see we're going to travel across a number of different terrain types. And again, each one of those terrain types is telling us about a different period on Mars. One of my favorite photos is this, though. It's context. That little speck that you can see, or maybe not see, I can barely see it on my computer, is Earth. It's about 3 pixels wide. So if you're a fan, it's not very big. But yet, Earth is actually very close to Mars, relatively speaking, in the sense of our solar system. So Mars is about 50% further from the sun than Earth. As I told you, some of those daytime temperatures, cold, but not unbelievably cold. There's definitely places on Earth that are colder than that. The gravity on Mars is about 3/8 of Earth's gravity, so it's, you and I could walk around fairly comfortably on Mars. And, 4 billion years ago, there was water on Mars. And it was habitable water. So the question is, why then is Earth so unique compared to a planet that really, when we talk about our understanding of planets, is really very similar to Earth? And so that's one of the reasons why we explore Mars, is to kind of put our own planet into context. Why is it that life is, so prevalent here and not on this neighboring planet that in many ways could have been very similar to us? And that's one of the questions we seek to answer. This is actually one of the very first photos we took on Mars. It's about 4 p.m. the day of landing. We defined a local Mars time. But 4 p.m., where Curiosity landed, you can tell the sun is kind of setting. Earth has already actually set for the day. So we won't be able to see the rover directly from Earth, but we have talked to it from the orbiters. And the shadow is cast, and we happen to land beautifully looking at Mount Sharp. And Al Chen, who was the voice of landing that night, says, "Touchdown confirmed. Let's see where Curiosity will take us." And I love this sentiment because it's not just about Curiosity, the rover, where it will take us, but ultimately our human curiosity. Where will the curiousness of us all lead us to be? What questions will we want to answer about the world around us? What will we want to solve? And I think that's a beautiful way of kind of perceiving the universe, let's be curious, let's ask questions. And so, in that note, let me tell you a little bit about the questions that NASA is going to be asking in the next couple of years. One, we just had a mission arrive at Mars. I mentioned that there's 7 missions at Mars now. We jokingly say that Mars is the only planet entirely inhabited by robots. It's true. And we had actually not only an American mission just arrived there, but also an Indian mission, which is really incredible. So that brings the grand total to 7 missions at Mars. MAVEN actually carries a very similar instrument to the mass spectrometer that we carry on board. So it will actually measure from above the atmosphere of Mars and help us to understand why the Mars' atmosphere is so different than ours, and also how it evolved over time. In 2016, we plan to launch another mission to Mars called InSight. InSight is built off of a design that we've actually done twice now. One time was successful, one time failed. But we'll reuse it, land near the equator, and look for basically activity in the core of Mars. So we know Mars doesn't have a magnetic field like Earth. It's also a little cooler than we might expect Mars to be, so we're trying to understand why the Martian environment is different. And so those 2 instruments will actually be contributed by France and Germany. And then in Mars 2020, our kind of big flagship mission again, that will be very much like Curiosity. And we'll carry a handful of instruments, one, to look more for direct evidence of life. Now that I can tell you that, yes, Mars could have supported life, the question is, did it support life? In addition to that, we'll also carry in situ resource utilization instruments. So those are instruments that are designed to take advantage of Mars, meaning that we will, one of the instruments, for example, will take the carbon dioxide that we see in the atmosphere and try to turn it into oxygen. So if you're a future mission to Mars and you want to build rocket fuel, you'll want that oxygen. If you're a human on Mars, you will definitely want that oxygen. And so the hope is to build this suite of instruments that we know will work on Mars and hopefully build for the future of Mars as well. And the other thing that we'll do looking towards the future is called sample caching. And that's where this rover will actually core out parts of the rock, and we will take that core and put it inside the rover. And the hope is that a future mission to Mars will be able to grab all these really interesting things that we've already looked at and bring them back to Earth so that the best laboratories that we know of can take a look at them and understand Mars. But beyond Mars, we're headed out to the end of the edge, I guess, of the terrestrial planets. We're headed to Pluto, so that'll happen this summer. It's going to be the first time we've ever had a mission go to Pluto. What's really exciting is that just literally yesterday, the team of New Horizons team found an object in the Kuiper belt, which is a kind of a belt of comets and asteroids that sits beyond Pluto, that they can actually target once they fly past Pluto. So it'll also be the first mission to ever look at a Kuiper belt object. At that distance, I should say. Sometimes we see them as they come into Earth or towards the sun. But that's amazing, and that's happening as we speak, the planning for that. And then in 2016, we'll send a mission to Jupiter called Juno, and Juno will actually be orbiting very close to the top of the atmosphere of Jupiter, measuring the atmospheric composition and trying to penetrate below the top layers of the atmosphere. Each one of those solar arrays is about the size of a tennis court. It's a very big mission. Solar power doesn't really work very well beyond Mars, so we have to make these solar arrays very large to work at Jupiter. That mission will last for only about 3 months because we know we're so close to the atmosphere that we're going to slowly get caught by the atmosphere and pulled in. And then the mission that I work on, Europa Clipper, which is scheduled to launch in 2022. Europa, for those of you who don't know, is a second moon of Jupiter. What's incredible about this is that from the data we have from Voyager and Galileo is that we can observe that there's an icy shell, what appears to be a liquid water ocean underneath that, and salts and chemistry dissolved in that ocean. And it's kept warm by tidal heating from Jupiter, meaning as it orbits Jupiter, it actually gets kind of squeezed and relaxed a little bit, so it slowly warms up. So on Earth, where we see, of course, near the ocean floor, that there's hydrothermal energy and water and chemistry, we see life. And so the hope is that maybe these moons, these water-bearing moons, like Europa, like Enceladus, Saturn, could also be places that life could arise. So the hope with the 2022 mission is to investigate further into Europa, understand where the ice stops and the water begins. If we're lucky, we'll see maybe a little bit of the rocky core. We'll be able to tell the chemistry of Europa. There was actually a paper that just came out last month showing that there are plate tectonics on Europa, that the ice on the surface is moving. That's the first place that we've ever found that outside of Earth. So if you can imagine, sometimes these odd moons of other planets can actually be more Earth-like than our neighboring planets. And then, of course, there's the human spaceflight side. So NASA announced the awarding of 2 contracts to Boeing and SpaceX to basically develop human flight capsules to go to the space station, to what we call low Earth orbit. The idea for NASA here is that we would love to move beyond low Earth orbit, and so much like we now fly across the country by buying a ticket here and there, NASA could buy a ticket on one of these capsules in the future and just take a ride like you would on an airplane up to the space station. And then to go beyond Earth orbit, we have the Orion crew capsule. This is designed for long missions up to about 28 days long. And here people could, sit inside here, go to the moon, could go to nearby asteroids and things like that in order to have some presence and expand beyond kind of our near-Earth orbit. Also, in the long run, they hope to expand the capability beyond 28 days. So maybe multiple crew capsules could be used to maybe fly a mission to Mars. And getting beyond Earth orbit also requires larger launch vehicles. So in the 60s, we had the Saturn V vehicle. This is a space launch system which will actually be more powerful than the Saturn V when it's fully developed. It will also allow us to travel humans beyond low Earth orbit. It also means for a mission like Europa Clipper that I work on, if we launch on this, we can get to Europa in about 2.5 years. With the current best rockets that we have, it'll take about 7 years to get to Europa. So the difference between me not being retired when we get to Europa and still working is maybe the difference in this rocket. And then beyond that, one of the ideas that we have for missions is a kind of a joint robotic human mission is to capture an asteroid that's already kind of headed in towards Earth and then bring it and deflect it and move it into orbit around the moon. I promise you it will not be like the movie Armageddon. It should be very safe. And the idea is once it's there that humans could go visit this asteroid. From a scientific perspective, we love this because asteroids are often made up of the same material as planets were in the early days. So it's kind of this early, look back into history of planetary formation. From a kind of a future perspective, one experience of going to the asteroids will help us in terms of planning longer missions to Mars. But also, it will help us in what we hope is one of the key industries of the future, which is mining asteroids for resources. So as opposed to constantly kind of digging up our own Earth and making a mess here, hopefully the idea is that we can take stuff from space and bring it back to Earth safely. And then ultimately, the hope for NASA is to send people to Mars. And that's kind of, we're hoping going to happen in the 2030s. So many of you guys will be, around to see that. Some of you guys may be even young enough to be one of the first people to go to Mars. But right now, one of the big challenges we have is how do we get back safely? So we know that we could do a one-way trip to Mars. It's technically feasible, but NASA is in the business of bringing people home safely. So we won't do a mission to Mars until we can, basically say we know how to get you guys home. And that's going to be a real challenge. With missions like Curiosity, we land for every kilo that we launch with, only 1/4 of that makes it safely to the surface of Mars. But imagine now you have to take that 1/4 and bring it all the way back to Earth. You're looking at maybe for every 20 or 30 kilos you launch with from Earth, only one of them can make it back. So it's going to be a real challenge. How many launches will it take? What do we need to have ready for the astronauts when they land? Should we have all the food supplies ready for them so that we know everything is working when they get there? Do we bring it all with us? And those are some of the questions that NASA hopes to answer. And that's basically the hope for space. So with that, I open it up to you guys for questions. I hope there's lots of them. I love questions. It's my favorite part of the presentation. So, thank you. I see one.
So as Bobak said, he will be very happy to answer all questions. So
Yeah.
Thank you. Okay. Again, thank you so much. Also, the American Corner, thank you for making this possible. Well, it's really exciting. I mean, I really don't know how to, phrase this. It's one question. I was interested in the fact that, for instance, the new mission that's based on Curiosity is going to build up and it's going to use instruments that you work in situ.
Yes.
So is there somehow, for instance, I also know that considering that like the Made in Space company is bringing the 3D printers to space and trying to make the space manufacturing a business or some sort.
Right.
Is this like an option for NASA, or is it more relying on third party, like SpaceX and how do you think about it? Yeah.
Yeah, I mean, the future of NASA is a little bit interesting because we do have a commercial space program that's starting to grow. And not just, obviously the large companies like SpaceX, but like you said, Made in Space, which is building 3D printers that would, work in that environment. There's companies like Planetary Resources, which want to mine asteroids. They're obviously still starting on understanding how to do that from an architecture standpoint. I think the future of NASA is what we would like to see is NASA being able to transfer the stuff that we kind of do already, so low Earth orbit, International Space Station, potentially 3D printing at the space station, and transfer that to commercial enterprise. And that hopefully will free us up to go off and do the crazier things like looking at asteroids, going to Mars and stuff like that. So it's kind of a balancing act. I think as we sort of mature ideas and technologies, we hope that commercial industry will find ways of using them for, maybe it's for space tourism. Obviously that's going to be a growing market. But also maybe manufacturing in space could have some advantages in microgravity. There may be some strong things. We've definitely done a lot of research like that on the space station. So always the hope is that we kind of build things and then, smart people here on the ground realize that there's clever ways of using them. So I think that's kind of the hybrid that you'll see in the future, continued in the future, but maybe even larger because these companies are really taking off for the first time on their own. Yeah.
Okay, thank you.
Yeah. Other questions?
Sure. What's the lifetime like for the Curiosity, and what are the repair capabilities?
What was the second part of that?
Repair capabilities.
Oh, okay. So Curiosity's lifetime, like most of your electronics, we have a warranty. We guaranteed that we would work for 1 Mars year, which is a little less than 2 Earth years, 687 days. We've passed that already, so we're still working, which is great. In 2004, we landed 2 rovers. Both had a warranty of 90 days. We're talking Martian days, so sols. One of them we lost in 2010, so 6 years. And the other one is still going. It will be 11 years in January. So we have a pretty high standard, even though we say the warranty is only a short period. Curiosity is a little different. So one of the amazing things about the 2004 rovers is they were solar powered. And we thought, okay, what's going to happen is after 90 sols on Mars, the dust will slowly settle on top of the solar arrays, and we'll just have less and less power until we can't use it anymore. Well, Mars always has some tricks, and so we realized for the first time that there are these dust devils. So you might see them if you ever go out to the desert or to really dusty areas where there's not a lot of water, and you'll see like these little small tornadoes where wind is spinning around. And we realized Mars has those, and every once in a while, one would come near the rover and would just clean off the solar arrays, and all of a sudden we'd have all this power. And we're like, oh, this is great, this is gonna keep working. With Curiosity, we're nuclear powered, we're not solar powered. And you might ask, well, why would you do that when you realize solar power was so good? One of the drivers for Curiosity was, I mentioned a little bit about how we had shrunk the landing area from 200 kilometers down to about 20 kilometers. One of the drivers for that was we wanted to give the science team as much flexibility or possibility in choosing wherever they thought was the most interesting place on Mars to go. And that included opening it up from the equator, which the previous missions could only land near the equator, to going all the way to plus or minus 45 degrees latitude. And so once you get past the equator, really, if you're there with solar arrays during the winter time, you just don't get enough power to stay alive. So we had to go nuclear power. Now we ultimately actually landed, Gale Crater is right near the equator, so we could have had a solar mission. But when we said this choice, they actually didn't choose the landing site until a couple months before we launched, at which point we already built a rover. So the nuclear power source is pretty good. It's 110 watts right now. It will slowly decline over time to the point which in about 10 years we think it will no longer provide enough power to make daily operations easy. Whether people find clever ways of doing other things with it, whether we wake it up for weather station reports or other things, there may still be a chance of using it past then. Otherwise, we think it's pretty robust. Things like the wheels are obviously seeing some damage. There are parts of the rover that are what we call single string, meaning that if one part of it fails, that whole part of it fails, like the arm. There's only one arm, we don't have a second arm. But the computers on board are dual strings. We have 2 sets of computers, so if one fails, we can go to the other one. So we think we have a good 10 years, hopefully, in this mission from the start, yeah. And I can tell questions too on my own.
This 2 megabit per second data rate is the link between the Curiosity and Earth station, or?
The 2 megabits per second is the link between us and the orbiter. Is that what you're asking?
Okay, is the communication link between us and Curiosity?
The communication between us and Curiosity is 800 bits per second. That's at close Earth range.
Okay, and how long have you driven on Mars so far?
Oh, how far? We've driven just around 9.5 kilometers.
Okay, thank
Yeah.
you.
There's a question in front, yeah.
The man on Mars, how many years that you think that it's possible we put a man on Mars? 20
Well,
years, 14 years,
yeah.
in the next century?
It's a great question. It depends on who you ask. And I think if you ask NASA, like I said, our goal is to send someone there and bring them back, which we believe is possible, I mean, with politics and money aside, is possible in the 2030s. So you're 20 years from now. If you are Elon Musk or Mars One or some of these companies and you are willing to do a one-way trip, I mean, I think that's possible within the next 10 years. Technologically, getting there and putting stuff there is very doable for us. But really, like I said, the hardest part is how do you leave Mars? How do you land enough stuff there that you can bring people back safely? And that's very tricky. Yeah. Some questions in the back. Yeah.
Hello, thank you for a very nice talk. It was really interesting. So I have 2 questions. First of all, which type of antenna usually they use in this type of robots or a spacecraft? I mean, which type of concerns they have to build an antenna? And another question is that which type of cables you use to transfer data? I mean, not just in a small robots, in the spacecraft, for example, it is coaxial cables, fiber optics, or because I don't know what is the concerns there.
Sure. I actually don't know what kind of cables we use. I didn't work on the cabling. I mean, they're copper wires. They're not fiber optics. In terms of the telecommunications, we have the 2 ways of talking to Earth. So one is an X-band radio, so that's microwave frequencies, and the other one is UHF radio, which is what we use terrestrially pretty often. The UHF radio is used for a link with the orbiters. It's the lower power of the 2. I can't remember. I think it operates at 5 watts or something. It's pretty low power. And the X-band radio is about 17 watts. And that's a phased array antenna, so it's essentially a flat antenna designed with a pointing of about 1 degree. The UHF antenna is omnidirectional, so it just sits on top of the rover and it can talk to any time the orbiter is in the sky over, above the horizon. Yeah.
Hi. Hello. What do you think happened to Mars?
I have no idea where I'm looking. Okay, thank you.
You said that Mars had water.
Yes.
And what do you think happened to that water?
So great question. So like I said, maybe 4 billion years ago, Mars had clouds and water and maybe looked a lot more like Earth. We can't speak, of course, to whether there was plant life everywhere, but certainly a little more Earth-like. There's a number of things that could be the cause of that. One of them, of course, is we know Mars doesn't have a magnetic field, which means that without that protection, the solar winds will slowly erode the atmosphere. It also doesn't have quite the gravity of Earth, so it can't keep the atmosphere as easily. But the other part of that is it's very clear from a map of Mars, and I feel like this question comes up and I should have a picture of Mars in my presentation, I don't. But if you look at a map of Mars or a globe of Mars, it's very obvious at first glance that the northern hemisphere is a lot smoother and it's a lot lower than the southern hemisphere. And what that tells us is that somewhere in that period, after the period of what we call heavy bombardment in the solar system, meaning where there was asteroids and comets and they were flying around and smashing into the things. So like when you look at the moon, you see this period of heavy bombardment, you see a lot of craters. Somewhere after that, there must have been a very large catastrophic event at Mars where the top part of Mars must have lost a lot of material. A lot of it maybe went to space and a lot of it came back and settled, but only in the northern hemisphere. So that's why the northern hemisphere is much smoother than the southern hemisphere. So it could be one of those things that caused the loss of atmosphere. But that's one of the reasons why MAVEN is there. So that mission is going to help us understand at what rate the atmosphere is lost on Mars. And maybe that'll allow us to answer the question of what caused the big loss. Yeah. Other questions?
What do you think is the biggest obstacle that's sort of declining human presence in Mars?
Well, I think seriously the biggest obstacle is money. It's always money because these things aren't necessarily immediately profitable. We don't know, of course. I mean, many of the technologies that could develop will probably have ramifications here on Earth. But always it's a question of whether governments and everybody else want to spend that kind of money to send people to Mars. I think that even with a Mars mission like this in the 2030s, it's going to have to be a very international mission. That you're going to have buy-in from multiple countries, and that all those countries will be contributing. That's really, honestly, the best way to guarantee the success, because what happens otherwise is sometimes if a new president or a new member comes in, they'll decide to change the plans. But if you have a lot of international collaboration, it guarantees that these things will continue past short term. Yes, I see it.
What is your opinion on the Mars One project, and does NASA support it in any way?
So the Mars One project, for those of you who don't know, is a Dutch company. They have stated publicly that the goal is for them to land 4 people, I think in 2025, and 4 more people 2 years later. It's a one-way trip design. It's from an architecture perspective, meaning from what they've published, I would say that it seems very feasible. I mean, all the steps are the right steps. And they have some demonstration technologies kind of in work. However, I mean, they also say that they can do it for $6 billion, which strikes me as a very low amount to send people all the way to Mars. And I know that part of the way they're paying for that is through a reality TV show. So you will be able to follow along as hundreds of applicants slowly are eliminated. And then 2, you'll be able to watch cameras on board like Big Brother. I said this jokingly, but it also scares me a little. My biggest fear is that for some reason they make it to Mars and then they start running out of food and have to eat each other. And then it becomes the most popular reality TV show of all times. To answer the second part of your question, I don't know, honestly. As an engineer, I want to see more information to always make a call. So I can't really tell you how far along or how successful I think they'll be. I mean, I wish them the best of luck. I want to see people on Mars. As much as I'd love for NASA to be first, I would much rather see us make it to another planet. The second part of that is NASA involved in any way. I don't know specifically. I haven't heard what involvement we have. I know that there's another group called Inspiration Mars, which is founded by a gentleman named Dennis Tito. Dennis was one of the first, I can't remember, first American, maybe, space tourists who bought a ticket to the space station for $60 million. Interesting thing about him is he actually used to work at JPL, where I work. Obviously was not getting paid $60 million, but what he did is he took the tools that he built at JPL, essentially a process of evaluating where money should be spent on technologies, took it to Wall Street, invested in stocks, made so much money, and then was able to go to space himself. So he did it right, I think. I know that he's involved with, example, for NASA Ames, which is one of our centers in the Bay Area. So I know that they're connected with him, but I don't think that, for example, the laboratory I am at is connected with Mars One, but it's possible they've reached out to folks at NASA, and I'm just not aware of it. Yeah. Other questions? I'm looking, there, yeah. Well, you're raising your hand, but who has the microphone? It's over there. Okay.
You said, like, with Curiosity, you left a lot of stuff in the Mars surface. Are you ever planning on going back and maybe reusing that material and getting it back to Earth in order to reuse it, or just you're going to leave it in Mars?
Maybe I don't think I completely understood the question. Is the idea to reuse Mars stuff, or to
with Curiosity, for example, you left a lot of stuff in Mars. Are you
Yes.
ever planning on getting it back to Earth and maybe reusing it?
No. So the Mars, everything that goes to Mars, because they're not humans, is one way. Eventually, the idea is to have a separate mission that will do sample return. But sadly, I would say that I've probably seen Curiosity with my own eyes for the last time, in 2011. My hope is that one day, at best, my hope is that one day, if humans are at Mars, that we'll have like a little museum around Curiosity, and that I'll be able to visit, or that maybe somebody, if we're lucky, will bring back a small piece and it'll be at one of the museums in the world. But I don't foresee us doing that. These robots, oddly enough, you become very close and attached to them. And so it is really sad, actually, when you think about, like, oh, I'm never going to see it again. And eventually, it just very quietly kind of goes to sleep. I mean, you basically send the last command, and you tell it, shut down, and that's it. Like, it's done. So it's a little sad when you think of it that way. Yeah. Yeah. Nope. Oh, there it is.
Okay, sorry. My question is about the solar radiation between Mars and Moon, because we already sent some people to the Moon, and you said that the radiation in Mars is a bit harmful to humans. The astronauts that went to the Moon, did they had that kind of hazards too, or the radiation levels there are a bit lower? And do we already have the technology to shield the astronauts for that kind of radiation?
Good questions. So all the astronauts, including the ones even in Earth orbit, actually experience a significantly higher radiation environment than we do right here. In fact, when you're on an airplane, you often experience a significantly higher radiation environment than you do here. I can't remember how much flying it takes, but I believe somewhere around a day worth of flying is about the equivalent of having one X-ray. The lunar astronauts also saw it, but over the course of a week, it's not as bad. Even the space station astronauts who are up there for up to a year, it's within what we consider acceptable levels. So it's not too bad. What happens with Mars is that you have to go for, the travel time there is usually at least 6 months, if not longer, and the travel time back would be the same. Plus, you have a period that you want to stay at Mars, and so that's the real issue. So in terms of protecting them, there's a lot of people who have different ideas. With space, always the concern is how do you minimize weight? And so the answer usually for these protection is, for robotic missions, what we do is we build a shield around the sensitive electronics like computers. And it's basically a layer of aluminum or a layer of lead or tungsten or something that will absorb the radiation, the energetic particles. With humans, you can't put enough of that around to protect them because it weighs too much. So the idea is typically to take things you already have and put them on the outside of your vehicle. In this case, a lot of it would be like maybe putting the water that they need on the outside. Some concepts have them putting the diapers and other things and stuffing it into the walls. That's kind of gross, but it's doable. And then a lot of them also include inside of the actual travel module a small section at the center that's more heavily protected, that if there are solar flares, meaning like specific events on the sun, that they can stay in there for a few hours during peak periods of radiation. So it wouldn't be where you would live normally, but it would at least be where you could, stay and be protected for a little bit. Yeah. Good questions. Other questions at the top. Yep.
Hi, I have two questions. First, how come your rover specs are so weak compared to current technology? And second, how do the electronics cope with the Martian weather, the fine grain, and such?
Sorry, I missed both of those.
First, how come your rover specs are so weak compared to current technology?
What kind of?
The specifications, the electronics.
Yeah.
And second, how do the electronics cope with the Martian weather and the fine grain that's in the air and such?
It may be the acoustics, but it's really hard for me to understand the second question too.
Like the Martian weather is really dangerous to electronics.
Yeah.
How do the rovers cope with it?
Yeah. So it's a good question. So the atmosphere on Mars is, like I said, it's about 1/100th of the Earth's atmosphere at the same so-called sea level. Early missions, like the Russians, actually, what they used to do is they would put all their electronics in a sphere and seal it at 1 atmosphere of Earth, so they would work. Our electronics are designed to handle the vacuum of space, so all the materials that we use are designed not to outgas, which is essentially, outgassing is like what causes that smell in the new car. It's where plastic gives off a little bit of its stuff. So all of our materials are usually baked out first so that they're actually put into a vacuum environment and we get rid of any of that stuff that's left. They're also all space qualified, meaning that we buy them usually from BAE or other vendors like that, like Raytheon, who build electronics that are designed to work in a vacuum environment. And I think was the other question was, did you catch it? Oh, so yeah, we'll go back to that picture. I like that one a lot. So when I'm going to burst your bubble. Sadly, even the 2020 mission is not going to look much better than Curiosity. What happens with space technology is that there's two things that happen. One is that we tend to build these computers or have them built several years before we launch. So when we launched in November 2011, by that point we already had the computer selected for at least 5 years. And the reason for that is you want to start writing code for the computer, you want to start integrating hardware and software, and you want to be able to test all that in time before you launch. So what it comes down to is essentially that we have a test program that needs 3 or 4 years of testing to say we've gone over every scenario that we can think of, good or bad. So we picked a processor, basically a 2005, 2006 space processor. And then when I say space processor, I mentioned a little bit about it, but all these processors that we pick from have to be space qualified. So that means they have to be designed to work in the vacuum in the space. And the key there is actually the same thing that came up earlier, is the radiation. What really destroys your electronics in space is radiation. So in a normal case, your electronics were protected by the sun. It's also very easy for you to, theoretically, to fix it. We can't obviously go and fix our rover. So what happens is these energetic particles like radiation come in, they will hit a part of a circuit board or part of a chip. And what happens is what was previously a 1 becomes a 0 or vice versa. If you're in the middle of a command, that can be very dangerous. Meaning if you were saying, let's open the thrusters or close the thrusters, and all of a sudden that becomes open the thrusters, that could end the mission. So we need to protect against that. In very severe environments, radiation can cause parts to seize. So essentially a transistor gate can go from one position that's open and closable to permanently fixed in one position. And so those are the hard things that we have to deal with. So in order to combat that, like if I took my phone in space, it actually probably wouldn't survive super long. So in order to combat that, we have these devices that are designed to, one, have correction built into them, meaning they immediately will try to detect if zeros have become 1 and vice versa. And 2, they make them essentially a little more robust to that. So it could be that they have slightly larger circuits or things like that where that energetic particle can more easily be dispersed as opposed to causing damage. So really, even in 2005 or 6 when we picked a part, it's really a part that was from 2003 that had been qualified for space. And the processors that we use, it's a RAD 750 processor. It's kind of like the same thing that you might find in a car or something else. So it's less cell phone-like and more what we call embedded processors. So the kind of processors that you find inside of things that, that have some smarts but don't need a, human user interface and everything else in the same way. Yeah. Yes.
One question I would like to make is, most of your experiments aboard the Curiosity are about the atmosphere and the living geology of Mars. So testing for some kind of life presence will always be indirect. So in a sense, you must have some kind of protocol to ensure that a potential positive signal of a life presence within the error bars, that usually the first evidence always comes within the error bars, and then triggers a lot of efforts. The protocol to follow that and ensure there is no contamination by some onboard bacteria or life presence that came, and sometimes they can survive actually quite long. So do you follow a protocol for that?
So one, I should say, Curiosity does not look for evidence of life. So we did that with Viking in 1976. We backed away from that and went for follow the water. Could Mars have been habitable, but not looking for evidence of life? And now with future missions, we would go and potentially look for life. What we follow is a couple of things. One, all of our results are usually verified not only by the science team at JPL, but usually peer-reviewed, of course, before they're published. So we do try to follow standard science protocol in terms of making sure that it's been reviewed from outside sources. In terms of contamination, decontamination, things like that, like I said, one of the things we did was to kind of rinse the system with Mars so that any presence of Earth would be diluted. But in terms of biological presence, we are always aware of that. So all of our missions, not just to Mars, but any place that's deemed potentially habitable, so not, for example, Jupiter, but the icy moons of Jupiter, all of those missions have to follow what we call planetary protection. And that's where we basically say, what is the probability that this mission will contaminate body X with Earth life? And in order to do that, there's two parts to it. One of them is how clean is my mission, and two is how likely is my mission to fail in a way that will leave biological material on Mars or on Europa. And so with places like Europa, actually, it's very hard to answer because we don't know how likely Earth life is to survive in that environment. With places like Mars, now that we actually have some data points, it's a little easier to know that eventually over time, anything that's left on the surface is going to die because of radiation. So we're not too worried that we're going to leave microbes on the surface. We still clean the rover very carefully because if we didn't land successfully and we smashed into Mars, we had the potential of burying into maybe a polar cap or down into below the top layer of soil, in which case there could be maybe water or something else, in which case we could really actually cause a scientific problem. So in 1970, when they didn't know much about Mars, they actually took the entire spacecraft, put it in essentially a bag, and then cooked it like you would cook a turkey to make sure that none of the bacteria survive. But we know it's never 100%. And so it becomes always a question of probability. And you show, I think it's 1 in a billion chance of contamination is what we strive for. So it's difficult. And we also know, for example, as I told you, you can tell that we were in Florida, even though we were all the way at Mars already. And that's, so we know that even the best job of cleaning and wiping surfaces and cooking things is not guaranteed to give you perfectly clean. So it's always a mix of numbers. Yeah, good question. Yes.
Hello. How do the nuclear power supply works on the robot? It's with steam generation?
No. So we have a nuclear power source that's powered by plutonium. What happens is that nuclear power source essentially internally is extremely hot, and the outside of Mars is fairly cool. And what we do is we have a thermocouple, which is essentially a device where when there's a gradient of temperature, it creates a voltage across the device. And so what happens is if you have a significant enough temperature, you can get a pretty large voltage. And where we have a voltage, we can drive current. So it's relatively passive, meaning there's no moving parts. It's not like a turbine or anything like that. It's entirely based on the fact that this stuff, as plutonium as it decays, gives off a great amount of heat, and we can drive that.
So is like.
So, who's going to ask the question? Here? Okay. It's here. Excuse me, I'm here.
Oh, okay. I didn't know if he was still continuing.
Most of the audience is composed of young undergrad students. I imagine that most of them are interested in following your steps. So my question is, what do you suggest them to do?
Great question. Well, one, I have always a handful of different ideas about one, I suggest always pursuing something you really enjoy doing. I really love my job, so it's very easy for me to spend a lot of time there and work there and enjoy the people that I work with and everything else. But two, if you think that maybe I want to do engineering or sciences, things like that, my advice typically is to sort of find a group of people who are sort of like-minded as you. For example, I know my strengths and weaknesses now as an engineer. I know there's some things that I'm good at and some things I'm very bad at. Like, for example, I'm not very good at math, although you might think that's a requirement. It's not. But by working in teams of people, we can all kind of play to our own strengths. So one of the things that I do now, for example, and I really encourage young people to do it, is I mentor a robotics team in Los Angeles. So it's a high school team that's kind of near JPL where I work, and those guys, who are from 15 to 18 years old, they're building robots that do often very complex tasks. There's some autonomy involved, there's controls involved, there's mechanisms involved and all these things. And they have to learn how to operate that, even though it's not as maybe complex as Curiosity, they do it in somewhere about 10 weeks' time. It's still complex enough that you learn a lot of the basics of engineering, and you really learn how to work in teams. And ultimately, what all these kind of crazy big engineering challenges and science challenges that we have they're always going to be a team effort. So learning how to work in teams and learning how to communicate in a team is probably one of the best things you can do. I would argue that it's probably better to have an okay engineer who's good at communication than a really brilliant one who can't get an idea across to his coworkers or her coworkers. So that's really important. And the other thing I always recommend in terms of early career starting advice is to remember that you are probably surrounded by people who want to do, or who are going to end up doing some of the jobs that you want to do. So for example, when I was in school, I was in Department of Aerospace Engineering. I knew I wanted to do aerospace engineering, and that at least, a couple of my classmates were gonna have my dream job. And it turns out that's exactly what happened. A guy who graduated the year before me got my dream job at JPL, Jet Propulsion Lab, where I work. And the year I graduated, I emailed him and said, hey, I really would like to work there too. Is there anything you can do? So remembering that is always important. Keeping those networks and keeping in mind that the people that you're around are very likely to want to do the same things, and one or two of them might be successful at it. That's a really good way to get your foot in the door. Yeah. Great question.
Good morning. Currently, the travel takes quite a few months from here to Mars or even to Europa. Do you have any new projects on how to make the travel faster, or are you just trying to improve the current technology?
So yeah, there's, in terms of the basically propulsion-like travel, obviously we have our own travel on the surface of Mars, which is extremely slow. But in terms of traveling between planets or things like that, we're a little limited. So one, to get out of Earth's gravity, right now we don't have essentially a better way than chemical propulsion. It's the kind that provides a lot of power in a short burst. But once we're beyond Earth gravity, there's basically electric propulsion. And electric propulsion has the advantage of being able to thrust continuously for extremely long periods of time, months, even years. And so actually the asteroid redirect mission that I was talking about, one of the goals for that mission is to demonstrate on a larger scale that we can build these electric engines. And those would basically, we would latch on to the asteroid and then continuously burn for a very long time to move the trajectory. So it's relatively low power, but because it can be integrated over a very long time, it's extremely efficient. And so we've demonstrated that in small scale. Around Earth, there's a number of small satellites that use electric propulsion at very low powers. And then we've demonstrated that even on interplanetary missions, like what we call Deep Space One, that was a mission that used electric propulsion for the first time for us. So, but putting that up to a scale where humans could use it or things like that, that's the thing we haven't done yet. And so that's, like I said, one of the hopes for this mission is that it would prove that technology robotically, and then eventually we could use that on human missions. Yeah, another one up there.
I wanted to make a question about sandstorms that you talked earlier. Can they be a danger to the equipment? Like you said, they could clean the machines, but can they also be an hazard to them, harm them?
So I caught a little bit about sensors, but it was a little quiet for me.
If the sandstorms, apart from cleaning the machines, can also be harmful to them, like break them or...
Can we break the sensors?
Yeah, can the sandstorms be harmful to the...
Can someone repeat this for me, because I'm having a... Sandstorm. Oh, can they also break the... No, so one of the things is at a pressure of 100th of Earth, the sandstorms are very weak comparatively. Even though the speeds are actually pretty high, they're very weak compared to Earth sandstorms. So you could stand in, 100 km/h, per hour winds and not feel a thing really. So it's very weak for us. Our cables are exposed, but there's no real weather on Mars that we're worried about cables being even damaged.
Over here? Over here?
Yep.
We've seen you in this adult crying video, and you showed us the ring you were responsible of. What is your precise task? What did you do precisely in the Curiosity mission to be in the command room and everything?
So I was tasked, so I was an operations flight director. Here. So I was a flight director, so my job for the most part was responsible for the whole safety of the mission. And then what we do is every week we would have a series of tasks to do between Earth and Mars. For example, for launch, there is a lot of just setting up the communications with Earth and making sure all that works. As you get further out, there's usually making sure things survived launch. And if anything didn't work properly after launch, you want to make sure that, that you maybe had some time to address that issue. And then one of the other things that we had is we actually installed software several times on the way to Mars. So we'd have to install software to the spacecraft. One time within about a week after launch, another time right before landing, so we wanted to land on a different version of software than we launched with. So activities like that usually take about a week because we have 2 computers on board, because the data rates are pretty slow, and because we're very cautious the way we do it. So what we do is we usually install it on one part of memory, we boot one of the computers onto that bit of memory, see that it works, then boot it back to the original version of software, and then look at the data afterwards, and then eventually, if we consider it good enough, we'll write it permanently to memory and we'll use it. We have multiple memory banks, so we can always go back to an older version if a new version is causing a problem. So as a flight director, my job was mostly to go through the execution of those activities with a team on console. The team depended on the activity, so if it's software, obviously there's software people on console. If it's an activity like a turn or a maneuver, we would have people like propulsion people on console, power people on console, thermal people to look at the temperatures. And so it would be to kind of organize that team. In terms of the development, getting this thing ready, my job was actually to do a lot of the testing and writing scenarios and cases. So I actually ended up, as a flight director, executing many of the procedures that I wrote a few years earlier. And those procedures include, for example, one of the bigger ones that I wrote was, we have 2 computers on board, and I needed a graceful way to go between one computer and the other, so we could actually operate the other computer for a week during cruise to make sure that it was all, safe to work if it needed to work later on. Another one involved, for example, doing one of the first turns that we did. So we have to keep the arrays pointed at the sun and try to keep the Earth within the antenna field of view. And so that's like a maneuver activity that I wrote. Another part would be actually working with the attitude control team to determine where the spacecraft is in space, and then also coming up with future maneuvers that we'd have to do. So that's most of my job. And then on the surface, I actually was a flight director for a while, and then I became an engineering uplink lead, which means planning all the engineering activities for the rover to do once it's on. I mean, it's a little different on the surface, but still similar in terms of organizing a team and writing procedures. Yeah.
Can what happen on Mars? Can what happen on Mars happen to Earth?
Can not super likely, but certainly, I mean, 65 million years ago, we had an asteroid that took out the dominant form of life on Earth. So it's very possible that there are still things out there that can cause a lot of damage. In terms of us losing the atmosphere and things like that, it's very unlikely because of the magnetic core that we have, the molten iron core that we have, is creating a magnetic field, and that protects us from just losing most of our stuff. But certainly, a large asteroid impact could happen, and that's one of the things that, there's a famous equation called the Drake equation, which describes how likely you expect to see life elsewhere in the universe. And you say, okay, there's n number of stars and n number of planets and so on and so forth, and what are the odds that each planet has life and it becomes intelligent? But one of the factors to consider usually in there is how likely is it that life survives and propagates beyond its planet. And so there's a lot of people who think that one of the reasons why we don't see more aliens is potentially because many of the aliens never make it off their planet, and eventually the planet's destroyed from outside causes, like an asteroid, or sometimes from inside causes. So maybe it's in our interest to make humans get to Mars, so we have not all our eggs are in one basket.
I have a question that is, what is the technology outcome of this project that can influence our life? Like in CERN, you get the internet,
well, you wouldn't, I mean, it's a very slow data rate, so you wouldn't want to use this for the internet. No, there's a couple of interesting things. So one, at a more simple level, some of the technologies that we end up having to use to manufacture parts, like for example, we work a lot with titanium. A lot of the titanium work that we've done at JPL has gone into making parts for cars as well as bicycle frames. So those are some of the more fun ones. The science instruments on board are actually what get used more often. So the fact that we have a laser on our rover that looks like this, that laser that can zap rocks. There's actually a power company now in Northern California that's using a modification of this to look for methane leaks. It's a gas, they use natural gas, so they're looking for methane leaks within their network using this laser. The Kemin instrument that's down there inside the rover, that's been adapted to something that you can carry around in a suitcase, and you can do two things with it. One is you can actually determine chemical composition of drugs, which you can at least maybe in the field, so somebody can have a pill or whatever or something, and you can actually determine that if it's what it is, what you expect it to be or what it's actually made of. And two, it's allowed for us to do what we call non-invasive analysis of artifacts. So we can look at things like paintings and stuff like that to see what pigments were used and information without actually destroying any of the source material itself. So those are often what we end up with. Yeah. One more question, I guess.
This is the last question, okay, in public.
But you guys are welcome to come up and ask questions for a few minutes.
I'm trying to do the same question. How the sandstorms are formed in Mars?
Oh, okay. So Mars has sort of an interesting dynamic. Like Earth, when the day to night change, the transition happens, there is a big temperature change across those locations. So actually, I don't think it's obvious in here. Let's see. I mean, I can tell a little bit of the story. It's not perfect. The instrument that tells us about the temperature on Mars also tells us about the wind speeds on Mars. And so what we can see actually from the day to night transition, really when the sun sets, is that there's actually what we call almost a global breeze. So as that temperature changes, there's a wind that blows. And we see it in the morning and we see it in the evening when the sun sets. So those events and the fact that there's local heating and features on Mars, meaning that some areas are going to get a little warmer, some areas are going to be shadow, creates basically a difference in temperature. And that once you have a difference in temperature, you can actually create pressure systems. And that pressure will eventually give rise to small winds. And if they are able to be maintained essentially from heating from the ground, they can continue over pretty long distances. We actually have a movie that we took with the 2004 rovers of a sandstorm forming and coming across the plains. But it's mostly the same things that happen on Earth, which is that there's usually a small wind that gives rise, and then that energy is added to that system from the sun, or from warmth, really. Yeah.
Okay, so I think we'll have to close now because some of you will have to leave. I think Bobak will be happy to still talk to some of you. If you decide to come here. Just as a last curiosity, do you have plans to change your hairstyle, or?
I do. I have to come up with something good for Europa, so I've got to figure out what it is. Okay. Yeah.
We look forward for that. Thank you so much.
Thank you guys so much for coming. Thank you.